So this afternoon, we're going to be covering how we understand variations in structure quality in the protein data bank. This will take two parts. We'll review first the Worldwide Protein Data Bank validation report coming out of the OneDep system, the single global software tool for depositing structures to the protein data bank. And then we'll move on to some additional features that are present on our research-focused rcsb.org web portal that provide access to validation reports and quality review in 3D, review of structure confidence in 3D, and also interactive review of bound small molecule, bound ligand quality. Next slide, please. The Protein Data Bank, the PDB archive, was established as the first open access digital data resource in all of biology in 1971. It has grown more than 30,000-fold from just 7 structures initially to more than 220,000 structures today. It's the single global archive for experimentally determined 3D structures of proteins, nucleic acids, viruses, macromolecular machines, etc. The PDB is managed jointly by the Worldwide Protein Data Bank regional partners listed here, along with 2 additional specialist resources, the Electron Microscopy Data Bank and the Biological Magnetic Resonance Data Bank, BMRB. All PDB data are validated, deposited, and biocurated using this global OneDep tool that feeds structures coming from the Americas, from Europe and Africa, and from Asia and Oceania into the Protein Data Bank system. Next slide, please. PDB structure quality varies. Structure quality depends on the experimental data that were actually used, that were actually measured to determine the structure, the method of structure determination, and a variety of other factors. There are well-developed quality metrics and tools for visual inspection that can tell you a great deal about structure quality. I want to emphasize during this introduction that the quality metrics and the tools come from the community. The Protein Data Bank is an archival data resource. We are not the data police. The Worldwide Protein Data Bank validation report is the product of consultation across the structural biology community, including crystallographers, electron microscopists, and NMR spectroscopists. So every structure that's present in the PDB has a wwPDB validation report associated with it. And as I was saying earlier, the rcsb.org web portal does provide additional metrics and tools with which to perform quality reviews that may be more tailored to your needs. And to emphasize the importance of understanding structure quality, on the right-hand side of this slide, we're depicting 2 structures, experimentally determined structures of hen egg white lysozyme, the very first enzyme for which a 3D structure became available. These 2 structures were obtained at comparable resolution limits, 2.1 and 2.4 angstroms respectively, using macromolecular crystallography. And notwithstanding the fact that they're similar in resolution limit, the quality of these 2 structures is markedly different. This color coding that's available on the rcsb.org website tells you immediately that the largely dark blue PDB ID 5 Hotel November Lima using the NATO alphabet is significantly better than the structure corresponding to PDB ID 5 Foxtrot 81. The reason for that in this case is differences in the underlying data quality. It's important for you as PDB data consumers, when you do searches of the PDB and encounter not one, but multiple examples of the same protein structure, that you are aware of the tools that you can use to distinguish higher quality structures from lower quality structures, and focus your efforts, your understanding, your analyses, your experiment planning, your hypothesis generation on the superior quality structures. So with this introduction, I want to reiterate that if you have questions, please put them into the Q&A or to the chat. And now we'll move on to the next slide, and I'll introduce the star of today's show, Professor Chenghua Xiao, who is a PhD in structural biology and also has a master's degree in statistics. And he's going to take us through the rest of the formal presentation, and then he'll be joined by members of our biocuration team who will help with the Q&A. So thank you again for joining. It's a great pleasure for us to be able to serve many millions of users worldwide. And I wish you all a productive and interesting seminar.
Okay, thank you, Stephen. To help you understand the quality of PDB structure and select the high quality ones, we have to understand the wwPDB validation. That is the process to assess the structural quality. wwPDB validation reflects the structural community efforts and collaboration in addressing the structural quality assessment. Under the coordination of wwPDB experts in the fields of all three major experimental methods, macromolecular crystallography, or MX, 3D electron microscopy, or 3DM, and MR, to form validation task forces and publish recommendations. Then wwPDB implemented the recommendations into the one-step definition and annotation system. In addition, ligand validation was discussed in a special workshop and was implemented and improved later. Just like Stephen said, I want to reemphasize that PDB is not in a role of journal reference. We only review the structural quality and point out the possible issues to the authors, and it ultimately up to the authors to decide what to do with the issues. For structures with significant issues, we'll add a caveat record. We'll also present the quality report to users so that users can review and decide what to do with the structure and which one to choose, which is the focus of today's webinar. A PDB structure is commonly referred to as a set of atomic coordinates for the molecule. These coordinates are checked against established chemical references on the proper range of bond lengths, bond angles, portions, etc. But the hallmark of PDB archive is that all structures in the PDB were resolved by experiments, and recent structures have associated experimental data deposited, including things such as diffraction data for crystallography, maps, half maps for 3DM, chemical shift or exchange for MR. We evaluate the quality of this experimental data, and most importantly, the quality and the goodness of fit between the atomic coordinates and the experimental data. Sometimes the quality of local features are critical for structure studies, such as the catalytic size or molecular interaction components. So there is local structure validation in addition to the global checking. And different molecular components are also validated according to their specific chemical characteristics. For example, polymers are validated on their residual linkages, and ligands are validated against a small molecule database in addition to the PDB. In today's webinar, we will primarily focus on the structures resolved by MX and 3DM methods. The wwPDB validation report was generated at different stages for different audience. Data depositors can generate the preliminary reports through the validation server or validation API before they even start application for a quick review. And when they start application, a preliminary report is also generated upon file upload, and which reviewed the structures and point out the potential issues for depositors to review and fix if necessary. After the structure is submitted, the biocuration team, which mostly PhD trained specialists, will review the structures in more details and generate the official wwPDB validation report. This is a report that usually accompany the manuscript review for some journals, or most of the prestigious journals. And finally, upon public release, official report is also generated for users to review, and in different formats so that a PDF can be read and saved for XML format can be programmatically parsed. PDB requires experimental data deposition so that structural quality can be assessed against experimental data. wwPDB validation report helps the journal during peer review process, and therefore required by many journals, such as those listed here. Here's the example of the report at the start, with a summary of the structures and validation slider right on the top. Then it goes into the details of from different perspectives. To start, I'll introduce the slider, which according to the survey, most of the audience today will review. It summarized the overall structure quality in 5 sliders. On the top is R3, which measures how well the overall structure agrees with the diffraction data for MX method. The colored bar from red to blue represent the distribution of R3 in the PDB archive, with the red at the worst end and blue at the better end. And the vertical solid bar represents the percentile of this structure relative to all X-ray structures. And the open box bar represents the percentile relative to X-ray structure at similar resolution. In this case, you can see that R3 0.209 is pretty good for the overall within the PDB archive, but is somehow in the low medium for the structure at this resolution. The next bar slider is class score, which, as name says, measures the average atomic clashes. And the next is the percent of Ramachandran outliers, which measures how many residues have unusual mentioned torsion angles. And similarly, the section outlier slider measures the percent of residues with unusual section torsion angles. Finally, the last part, RZ, measures the percent of residues which has insufficient experimental data support. Because PDB has this preliminary report and official report, so authors got a chance to review and correct potential issues. As a result, we have seen improvement of structural quality after OneDAP is implemented compared to the structures before the OneDAP implementation. And these improvements are also reflected in the 5 primary metrics. As you can see, the class scores, percent of Ramachandran outliers, percent of Rotem outliers, and RSC all goes to the better end slightly after the implementation of OneDAP. A validation report starts with a summary and validation sliders and goes into details sections of validation from different perspectives, including the validation against experimental data that is method specific and it will be expanded later, but the validation of chemical geometry against the established chemical reference is not method specific. If you open any PDF report, this validation is covered in the section of residual property report and molecular quality. This part of validation also covers the 3 middle sliders as we just illustrated. PDB structures are macromolecular structures, and macromolecules are polymers of proteins or nucleic acid. These polymers' chemical structures are examined by various metrics such as bond lengths, bond angles, the 3 primary indicators we just indicated, and chiralities. For RNA, the backbone quality is also examined. The assessment refers to the established reference for protein and nucleic acid here, and they're carried out by MoleProbability and some PDB softwares. Then the result is produced in the PDF report in the molecular quality section as listed here. And there's also a summary residual property plot, as you can see in this example. For this polymer, each protein, each residue is colored green, yellow, orange, and red based on the number of outliers. Green means there's no outliers, and yellow, orange, etc. for more and more outliers. And the gray segment indicator residue is present in sample but not model, which is common for PDB structures. The red dot Above some residue indicate the per fit into the electron density, which I will talk in later slides. Here's an example of asparagine 150. It has two outliers, which is why it's marked as orange. It has rotom outliers and atomic classes between two of its atoms, as displayed in this purple disk. Many PDB structures are complexes between macromolecules and small molecule ligands. During one-step deposition, authors designate the ligand of interest, or IOI, if it's the subject of study, especially for structures involved in the drug design study. For older structure without IOI designation, we also mark those microwave greater than 250 Dalton as potential IOIs. With the complex structures, the ligands are usually much smaller than the macromolecules and are usually diverse in the chemical features. So we choose the high resolution small molecule in Cambridge structure database as reference. Each chemical component, such as bond length, angles, torsions, or ring, is compared to those distribution in the CSD to determine whether the component is within a normal range or is an outlier. For example, a bond length and bond angle with RMIC greater than 2 are marked as outlier. And there is a summary for each ligand, indicating the average RMIC for all the bonds and angles in this ligand. And there is also a list of the components or outliers. In this case, this bond is greater than it should be. Further, the report depicts the geometry evaluation assessment in 2D graph with different color. For example, for bond length, the green color indicates those bonds within normal range, and the magenta indicates those outliers. And green color means that either the validation on this component is not applicable or there's insufficient chemical references. Over 80% of PDB structures were resolved by crystallography. So understanding MX validation means you understand most of PDB structures. As indicated earlier, the validation will assess crystal diffraction data itself, as well as the goodness of fit between the structural coordinates and diffraction data. The results are present in the section of data, statistics, and fit of model and data. And this part of the validation is also reflected in the two sliders on top and bottom, R3 and Rs as the outliers. Here are some of the experimental data assessment on some quality metrics. Diffraction resolution limit measures how far the diffraction can reach. The higher, the better. And the completeness measures how complete the experimental data is collected. A good overall diffraction data completeness should be usually better than 95%, except for special cases such as virus with high symmetry. R-merge and RC measures the consistency between the symmetrically equivalent diffractions, and the smaller, the better. The I versus sigma measures signal versus noise, and the higher I versus sigma means better quality of the data. Note that there are other data consistency metrics such as RP, MARIM, CC-half, which if you are interested, you can read the wwPDB validation document. Resolution is a primary diffraction data quality metric. It measures how far the diffraction can reach, which means how good the atomic spacing can be measured. Higher resolution usually indicate better identified atomic coordinates, as you can see from this comparison graph from high resolution to low resolution, where this coordinates is represented by the ball and stick model, and a green mass indicates the experimental electron density. The median resolution of PDB archive is about 2 angstrom, and so here is what you expect to see for most of PDB structures. We also see that since 1980s, there's no significant improvement in the median resolution limit, because resolution depends on the crystal packing, which is primarily on how the molecule was crystallized. In terms of overall goodness of fit, R and R3 measure the similarity between the observed structure factor amplitude and those calculated from the model. Lower values and smaller differences between the two statistics R usually means better. R3 is usually higher than R because it's calculated using so-called reflection not using refinement. R3 depends on the resolution. For normal structure at about 2 angstrom resolution, R3 around 0.2 is expected. And you can always look at the structure percentile standing in the slider. FOFC correlation measures the consistency between the observed structure factors and the calculated structure factor. The higher means the better. And the value is about 0.9 is usually expected. There are also other metrics you can look into the wwPDB validation document. In addition to the overall goodness of fit assessment, the RSRZ, that is real space R factor Z score, measures each residue's fitting into the experimental electron density locally and compare the fitting to the same type of residue in other structure at similar resolution. RSRZ greater than 2 means that the fitting between the local residues and the electron density map is not as good as the other structures and marked as outlier. The report also lists the RSRZ outlier in the table. And it's important to point out that the surface terminal loop residues may be of higher RSRZ because they are more flexible. Small molecule ligand in a complex structure are also validated locally by RSRZ. And another metric called RSCC, which is real space correlation coefficient. And the RSR score, which is real space R factor, measures the difference between the model ligand and experimental electron density, and the RSCC measures the consistency between the two. So the lower the RSR, the better, and the higher the RSCC, the better. In addition, for ligand of interest, the report provides a map model overlay, which you can see at the two cases here. The one on the top shows a good fitting for NADP molecule between the model, which represents the ball and stick model, and the maps in the gray message. And this one also had low RSRs and high RSCC. For the other structure, you can see the mapping between the model and the green meshes is not as good, with discontinuity on the electron density. And also the green and magenta bulky presence, which indicate the plus and the minor differences. Here, the RSR is also very high and RSCC is very low, which indicates this is a poor fitting and should not be trusted. In recent years, we have seen significant growth of 3D-EM deposition. So it's important to understand the validation pertaining to 3D-EM method. The experimental data for 3D-EM method are usually maps and half maps, and the validation reports are present in a section of as listed here. Together with the number of growths for deposition, there's also significant improvement in the resolution for 3D-EM method. As you can see from this graph, in about 10 years ago, the average resolution was beyond 10 angstrom, which means low. And in recent years, it had grown to better than 4 angstrom. The three maps above shows that with higher and higher resolution, you can see more and more details from this electron 3D-EM map. And ultimately, for iperferritin, a special case, you can observe the map at up to 1.2 angstrom resolution, which is truly atomic. You can see the fitting for each atom between the map and the model. And I want to emphasize that apoferritin is a special case with high symmetry and very high molecular stability, which allows researchers to get a very high resolution on this molecule. The 3DM experimental data assessment starts with a map review, in which the primary map is viewed as a projection from different angle at a center slice or at its largest variance, which usually means a molecular section. In addition, the raw map was also reviewed from the same perspective. And you can compare the primary map and raw map. In addition, masking is common in 3DM study, which can cut noise over the background. And the mask is also reviewed together with the maps. Please note that masking is not a fully objective process. From the deposited map, the reported resolution can be validated. 3DM resolution is estimated by analyzing the Fourier shell coefficient FSC curve, and FSC is generated from the 3DM experimental density maps. The FSC curve drops from low to high resolution, and the cutoff is decided usually at the 0.143, which is indicated by the green horizontal line here, to indicate the resolution estimation. Here you can see that the author reported resolution 2.40 angstrom, which is validated by the author provided FSC as well. The validation also calculated unmasked FSC from unmasked maps, raw maps. Then estimation from this FSC is 2.86 angstrom, which is slightly lower. The minor difference is expected between the unmasked and masked estimation because of the masking. Next, the map model overlay reviews the goodness of fit and also indicates the contour. And here, the blue ribbon indicates the atomic coordinates model, and the yellow half-transparent mass indicates the maps at the author's contour, where the misfit, which means the regions that is not covered by map, are the regions with insufficient experimental data support. Seeing the overlay is a good qualitative assessment, but we also need quantitative metrics. Atomic inclusion calculates the ratios of the atoms in the map density for each residue at author selected contour with an upper limit of 1.0 and lower limit of 0. 1.0 means all atoms of the residue are within the density, which indicate a better goodness of fit. The validation report also adds graphic depiction of this metric in different color, with cyan for higher inclusion and red or brown for lower resolution. Those residues with darker color, like experimental data support, and should be examined. Excuse me. Atomic inclusion is a straightforward method, but it depends on author selected contour, which is not objective. The other metric called Q-score was developed to avoid this dependency. It's calculated on each residue based on the atomic resolvability on the map without using contour. The atom resolvability depends on the resolution, so this metric works better for higher and medium resolution structures. The scale of Q-score is usually between 1 and 0, with 1 indicating better goodness of fit. And similarly, the validation report used the color scheme to indicate high or low Q-scores. Residues with dark colors are the ones like experimental data support and should be examined. Now I have gone through some fundamentals of wwPDB validation for MX and 3DM structures. I want to introduce how to use the report to select the structures. Among millions of PDB users, vast majority are not structural biologists. So it's important for us to help users to use the report to make the selection. Therefore, RCSP developed assessment tools. First of all, users should get access to the report. When you research any PDB structure, the landing page is called structure summary page. And at this landing page, you can see an experimental data snapshot, which includes fundamentals of the method, resolution, R-free, etc. By it is the validation slider. And above slider, you see the button that you can download the full report. You also see a button that you can review the structure in 3D based on the validation report, as you can see here. The 3D display is implemented in MouseStar, which is a fast and reliable 3D viewers embedded in the rcsp.org. And it has a feature of view the structures based on validation report and color the residue differently. For example, the blue color means the residue with no outliers, yellow means with one outliers, orange means two, etc. It also highlights the atomic classes with these purple disks, as you have seen before. And if you hover your mouse cursor over the residue, you can see that summary of this residue, including the quality assessment, as well as real space RZ score, which indicates the fitting quality. As indicated earlier, whether the structure is supported by the experimental data is of great importance for PDB structure. So we developed a confidence review in 3D, in addition to the validation report view. The primary metric used for this confidence is the real space correlation coefficient that measures the agreement between the residual atomic coordinates and the experimental electron density. Higher RCC means well resolved with high confidence. The per residue RC distribution indicate that the RCC fluctuated along the polymer, where you can see that a high value means high confidence is associated with this core structure, and some of the loops had lower value RCC, which means lack of experimental support. We also implement the 3D display user color scheme similar to the PLDDT local confidence score for AlphaFold computed structure models, where the blue means high confidence, cyan means good confidence, yellow means low confidence, and orange means very low confidence. The region with very low confidence marked as orange should not be trusted. The experimental confidence 3D view can be activated in MouseStar by clicking this button just next to the validation report view. And it can be combined with the map model density overlay, where you can see here. When the structure model is displayed in ribbon and the electron density map is displayed in the blue meshes. Here, 12FC is the commonly used map, and FOFC maps measure differences. Another common question asked by PDB user is how to find a high quality ligand structure. Ligand structure are very important for drug design and for understanding the molecular interaction. So we develop a dedicated ligand quality review to help users to select ligand structure of better quality. So what does a high quality ligand structure mean? First, it should have sufficient experimental data support. And second, should have good chemical geometry as well. But these are measured by multiple metrics. So we first reduce the dimension of the matrix so that we can demonstrate the ligand in a simplified view. We consolidate the goodness of fit metric into so-called PC1 fit by using the principal component analysis, and PC1 just means first principal component. And we do the same for chemical geometry matrices and consolidate into PC1 geo. These matrices are then ranked among all PDB ligands to gather relative quality standing in percentile. For example, on the right side is the standing of the PC1 fit, where you see at 99%, there's a very good fit between the model in stick model and the map in blue meshes. And with the percent going down, you see worse and worse fitting, and eventually a discontinuity of this electron density map. Once we have this PC1 fit and PC1 geo, we can use the 2D display, as you can see here. In this example, PDB ID 6WJC had 4 ligand instances of Y01, the ligand shred code. And the green diamond indicates the best fit ligand instance in this structure. And the green circle indicates the other 3 instances. The interactive table in the below, which corresponds to the graph, shows you all the details of the quality of the ligand, where you can see things like real space R factor, RCC, RMSE, bond length, etc. One ligand can be present in multiple structures. And to help users to choose the best ligand structure or the better one among multiple structures, we implement the comparison between the structures. In the middle graph is a comparison between the best fit ligand instance in this entry, 6WJC, versus the best fit PDB instance in other structures with the same molecular target, which means the same protein. And the one on the right is a comparison between this ligand structure to any other structures with the same ligand. And you can always see the detailed metrics in a tabular format in the interactive mode. To make this ligand quality review easily accessible, we also add a ligand quality slider just underneath the validation slider at the structure summary page, where the vertical bar indicates the ligand fitting quality that can be clicked, then lead to you to the 2D graph. And further, this 2D graph is also interactive with the 3D display, where when you click this ligand instance, it will lead you to the 3D display of this ligand overlay with the electron density map, where you can ultimately review the experimental data support. Now, if we want to read more into the wwPDB validation and how to use RCSP PDB, here are the resources. And we also have the PDB 101 training courses that we ran in the past and will run in the future that you can listen to and learn from. To summarize on the RCSP validation tools, first of all, from the structure summary page at rcsp.org, you can download the PDF report. If you want to do program parsing, you can download CIF and XML report from our FTP site. And on the structure summary page, there is this experimental data snapshot. And if you are a structural biologist, there is experimental type reading the details, which I didn't cover before. And for non-structural biologists, there is a sliders for quick overview. There's a slider for overall quality, also slider for ligand of interest. And the feature of MOSTAR 3D visualization has many useful tools to help you to do the selection based on structure quality. They can view structure by validation report features. It also can view by experimental data, experimental support confidence. And finally, it has this map model overlay to ultimately show the experimental data support. And we have the dedicated RCSP ligand quality page for MX method with the 2D and 3D interactive features for you to do the comparison among the structures for the same ligand. By no means I can give a full explanation of the wwPDB validation report in one webinar, but I hope I have covered the most fundamentals for you to understand and report and can use the quality indicator as discussed. This page summarizes such indicators. For example, if you're looking for a good structure, you are trying to find a structure with higher resolution, which usually means smaller value, and small are free, small class score, small number of outliers. And for ligand, you want a structure with the low RSR and high RCC. And for structure resolved by 3DM, you want to find structure with high Q score and high atom inclusion. So we have 5 minutes. I'll do a very quick demo just to show you where to find these features. I'm not going into the details of this report. So I'll just use one simple example in one of my slides. This is a PDB 6wJC. And once you search 6wJC on the top bar, it will lead you to this page, which is called it's sort of summary page, the landing page, where you see the experimental data snapshot as this demonstrated, and there is this slider. And above slider, you can download the full report, which will lead you to this report, as you can see here. And there are different sections, as I just introduced. There's overall quality at a glance, which means the slider and summary, the residual property plots, data refinement statistics, and under model quality, you see those that I introduced. And same thing with the topics under the feed of model and data. Further, you can click on the 3D report, which will lead you to this page, where you see the structure based on the validation report. And you can zoom on the region and hover over the different residue to see whether or not their geometric qualities, the real space RSRZ scores, etc. And under same as indicated, under quality view, in addition to the validation, there's experimental support confidence, where you can review based on the RCC values. And the blue means the good region, and orange just means the region that you should review or at least be careful with. And finally, you have this 1D ligand quality slider, where this indicates the best fit ligand of one type of ligand and another ligand, which is 101. If you click that, it will lead you to this page, where you can see that this is the 2D graph for the best fit ligand, and it's highlighted the row in the table, where you can read if you're a structural biologist. And you also do the comparison between this structure and other structure and structures in another structure with the same protein and other structure with any protein. And if you click on that, it will lead you to this nice overlay between the experimental data and the structure model. Please do take our exit survey so that you can help us to understand your need and design future webinars. Once you finish survey, you'll be able to, we will issue a participation certificate, and you will also receive a copy of today's slide deck. You can also register for other events in the future, and please go to RCSP website for further details. Finally, this is group RCSP PDB, led by Dr. Stephen Burley. RCSP PDB maintains the PDB archive and develop those features I just introduced today. We're funded by a combined grant from NSF, NIH, and DOE. And we're also members of the greater wwPDB organization. And here concludes my presentation. Any questions? And Jasmine is our annotation lead. Team lead, and she will charge in the question.
Thank you, Chenhua. There is a question. What is a good RSCC and RSR?
Okay, I can answer that. So if you go back, I will just scroll back to the part that is. I'll go back to the validation part then. So this is good, this is bad, everybody can see that. But like, if we want to set a boundary for ligand, for RSR, I would expect something at least below 0.3, means okay, better below 0.2. And for RCC, I personally always expect something greater than 0.9. Did that answer your question?
I think so. The same person, this is from Nian Huang. He also asked if there is reference to this question.
So we have a couple of PDB validations that you can refer to, and this is my publication summarizing the quality metrics of in the PDB archive in terms of RSR and RCC. You can also cite the wwPDB validation paper that also describe what is kind of good and bad RSR and RCC. That is in the resources. This slide will be shared with you, so you will see that.
Okay, thank you. There is one question that was already answered directly to the participant. I think it's worth to also let the rest of participants know the question and answers. PDB encouraged to submit the raw diffraction images. I submitted the new image in Zenodo. However, they are not cited by the wwPDB. Curious to know how where it will be implemented. And the answer is during deposition. Depositors can provide the DOI of the raw diffraction image set that you have deposited during the deposition, and then it will get recorded in the public MMC file. The other question also worth answering here is, I often see a poor RSRG score for residues. And when I look at the structure, there is no electron density for the side chain. Is this just the flexibility? Can anything be done, or do you just accept the density is poor in that region? Greg, do you want to provide the answer, please?
Oh, yes. I did make write in response to that question. There are two reasons for yeah, thank you very much. There are two reasons why you can have a poor RSRZ score. One could be the poor modeling. The density is not modeled correctly. Another reason could just be you have an extremely flexible portion of the protein, so the B factors deteriorate the electron density. Especially if the resolution's poor, you have data limitations. So therefore, it could be poor modeling, or it could be something out of the control of the person who solved the structure. So we just send the report to the depositors and let them review the density, and they make the decision whether this should be revisited, or whether they want to omit the side chain, or whether they feel it's best to include the side chain. That's their decision. We don't make that decision. But you can always download the structure factors and view the map if you ever want to judge yourself.
Yeah, just to add to Greg's comments that as a crystallographer myself, I was that usually if you look at a region and in the electron density map, if you really want to look into that, and the region is kind of flat without much density, it usually means that region is flexible. But if you see very noisy, then there's density there, but in a different, that doesn't overlay with the model, it could mean that the structure model could have been improved. But as Greg said, we don't make that decision.
Thank you. The next one, what is the real number of qual-EM resolution? I have seen people use different methods to claim the structure's resolution. Justin will provide an answer.
Yes, thank you. Very good question. So for reporting resolution in cryo-EM, the 0.143 cutoff is the most commonly used criteria for reconstructions that are better than 10 angstrom resolution. But it's important to keep in mind here that this is a global resolution estimate. And really, there's no substitute for taking and inspecting by eye these density maps because the reported resolution is influenced by masking, which is something that Cheng-Hua pointed out. And then also, you can see that there's a lot of local variation in the resolution when inspecting the maps. If you have, like, for example, regions that are highly flexible. So, yeah.
Okay. Next question. Are there any upcoming plans to add radiation damage score to the MX structure report sliders?
Who do you want to answer, Katrin?
Why don't you let me jump in and answer that question?
Sure.
Would that be acceptable to you, Jasmine?
Yes.
Thank you. So at the moment, there are no such plans, but if you would like to provide constructive suggestions to the Worldwide Protein Data Bank leadership team, you can do that through the, I think it's info@wwPDB.org. We will consider those seriously in consultation with the experts in the community that we continue to work with on questions of structure validation, etc.
Thank you. Next question. What are the ways to programmatically assess the validation score for a set of structures? I think some of these values are reported in a structure's MMC file, but what if I don't want to download the files for a large list of structures?
I mean, if you want to do program and punch, and you have to have access to the data, and if you don't have data, I don't know how you can. For some of this validation thing, you can use our API service. Like everything has API access. For example, you want to find our free. One second. You can use our advanced search.
So I think the answer, Cheng-Hua, is that our APIs will probably provide most, if not all, of the information that Dr. Davidson is looking for, but possibly not all. And if you are unable to get access to all the information that you're interested in, again, please provide feedback to us. All feedback is good, particularly constructive criticism. And if there are features that, in terms of data harvesting, data gathering, using APIs that we're not currently supporting, we can certainly consider implementing those.
Yeah. So here the example that you can search our phrase better than, actually this is bigger than, should be greater than. Anyway, just use your advanced search and you can implement the programmatic search API, which you can see here. And you can download this as a code and run it in Python.
Okay, thank you. Next one, beyond the validation report, are there any other factors to consider when choosing a structure for my own research?
As said, the report is a summary, usually quantitative and qualitative for evaluation of the structure. But ultimately, it's the structure coordinates and experimental data are ultimate determining factors. And if you can read into those maps, which is usually what I did, can tell you more kind of details about how well a structure is supported by the experiments and how good is this structure compared to data structure if you do the side-by-side comparison. And you can activate this map view at RCH doc through the MoStar as I just introduced.
I want to add that another factor one can consider is the completeness of the modeling.
Yeah.
Yes, and if you don't mind my adding also,
Sure.
Another thing to consider is what your research is and what your interests are. For example, if your interest is doing structure-based drug design, you might want to download the structure and the structure factors and look more in detail at the active site, the interactions between the ligand and the active site, and see whether or not those make sense. Or does the covalent linkage to the active site residue, does that make sense? And you might want to look specifically at those things, if that's your interest.
Yeah, and I think this MoStar viewer introduced some of these features for your research. It does have many other features I didn't introduce today. And in June, there is an event run by Shuqi that helps you to understand how to use MoStar if you register that.
Okay. Next question. What does a negative I think this is RSRZ score mean for a single residue?
I think you probably mean the RCC as introduced here. I think this is what you mean.
Okay.
You pick it up. So I think it's so this RSRCC is supposed to be between 0 and 1, but just like R factors in our merge now the things, there's an artifact for implementation of the formula. So sometimes you get some extreme values, which usually means it's outlier. That's it. I mean, it's just more RC, this negative RC is more artifact.
Okay. How are gapped PDB structures validated? How are gapped PDB structures validated? Is the output reliable?
I'm not sure I understand. Did anybody can answer that? If we...
I
Could
assume
Dr.
that
Egan
means...
please rephrase the question? I think that might be helpful for us.
Sorry about that.
Can Egan is the person who posed the question. Maybe you want to repost it to clarify what you mean. Do you mean unmodeled region?
Do you mean? Hold on a second.
While we are waiting for the participant to clarify the question, the next one is, I have a question regarding cryo-EM density fitting. Why my model is not fitting in cryo-EM map? The resolution is very high, around 2.77 angstrom, but I was unable to fit my PDB in the electron density of cryo-EM.
Okay, thank you, Jasmine. I'll take that question. It's another very good question. And it's a bit difficult to answer without having the details behind the problem, other than to say that it could be at least a few different reasons that cause issues with fitting. It could be that there are significant issues with the starting model that's being used to dock or fit into the density. And so if you have a starting model that is not very well predicted, for example, you can try putting that in the map and it's just a very bad fit and it's hard then to lock onto a better solution. I think also then you can have significant regions within the map itself where the density is poorly resolved and it can reach the point that it prevents achieving a good overall fit, or perhaps it's a local fit for a certain component where there due to flexibility or disorder. It's just very difficult, even in a well-resolved structure, to achieve a fit. Thanks.
Thank you. And Ken Egan has clarified he didn't mean the unmodeled region.
Oh yeah, I'll go back. You mean a region like this, right? Short answer is we cannot verify. You know, if it's a model, how do we verify? So, I think in that sense, we did have tools that can help you to do things like that if you are interested in the potential structures of that gap region, if I understand it correctly. So we, in the last seminar, CSM, computed structure model, Sebastian actually touched based on some of the tools that can help you to find the potential pose or conformation of the loops. But for these regions, usually we just, PDB archive is based on a set of coordinates. And if there is no coordinates, we can only refer to this part is in the sequence, but it's not modeled. And it will be up to the authors or the users to review the density map to see whether there's potential confirmation for that loops, etc. And if you want to understand more about CSM, how to use CSM to help you to model that kind of gap loops, you can review Sebastian's, last CSM seminar audios. It will be posted on PDB 101 page, which indicated in the resources page in this slide deck that it will receive a copy.
Okay, one last question. Is the 3D model validation tool available during deposition before PDB submission?
Yeah.
Answer is yes.
Here, this page summarizes what you can do. You can do the validation with a standalone validation server, but remember that when you get it, a preliminary validation report. That is not a report that some journal requires. And if we want to programmatic access, like you have 10 structures, 200 structures, you can do the APIs access.
Thank you, Chenghua. Thank you, Jasmine, and thank you to the rest of the team. And finally, thank you to the team behind the scenes that provided the logistics for this webinar. The RCSB Protein Data Bank thanks all of the more than 150 participants who visited us virtually for this webinar. Please feel free to register for the next of the webinars and watch our rcsb.org homepage for announcements of further outreach and education and training opportunities.